Hello friends, welcome to section 8, the final section of this hard surface modeling series. I hope you've learnt a lot throughout the series. I really aim to explain what is going on behind the scenes, so that when the time comes to apply what you have learnt, your strong foundation of knowledge will allow you to approach any modeling challenge with coordination and ease. This series has been tightly packed with loads of information on methods, workflows, tools, techniques, tips and more. As a result, we haven't had much time to practice modeling some real, complex machinery. And that is the goal of this section. Throughout this section, I will present various objects. You can attempt to create them yourself, but in case you need some help, I will have a sped-up recording of myself modeling the object, with a voiceover explaining any relevant methods. So let's get straight into it with the first set of objects, hinges. Hinges are probably the most common piece of machinery you would use for systems that rotate on one axis, for example knees and finger joints, as well as most types of doors and lids. There are basically an infinite amount of hinge designs. When you are making hard surface models, you should design your hinges to match the style and design of the rest of the character or object. Here I'm showing you a quad view of the hinge I'm about to make, which you can easily replicate by using the shortcut Ctrl-Alt-Q. These are references you can use if you want to try it yourself, but I will now be going through the modeling of this hinge and describe my thought process. I start by adding a cylinder, making sure to start with a lower resolution, and do some basic scaling and positioning. My main goal here is to set up a mirror modifier using an empty plane, as this cuts the workload in half. I extrude half the faces downwards, scale them to 0 on the Z-axis to flatten, and continue extruding until I have the basic form of the shape. I like to delete the bottom faces, since it makes it easier to add edge loops when preparing the model for subdivision. To cut the cylindrical hole, I can simply use the circle tool, insetting the faces in preparation for when I will need to add supporting loops. With the main features modeled, I add a subdivision and think about where my supporting and creased loops should be. These edges aren't fully selectable, as there are 5 edge poles where they connect to the circular area. I bevel them to add good neighbors, creasing the original edges, as well as creasing the loops around the cut. I notice that some of the edges extruded downwards are creating very shallow angles, and decide to loop them horizontally instead. I can then delete these vertical edges and merge the extra vertices. The last step is to bevel the horizontal edges, since I don't want the subdivision modifier to be controlling the curvature of the mesh. Finally, I fill the bottom face, making sure it has good neighbors, and that the original edge is creased. And there I have the final result, a perfect hinge with some interesting curvature to it. Now I'll make another hinge, only this time, imagine it is for a lightweight robot, so we are trying to minimize extra weight, whilst keeping the mesh sturdy enough to act as a reliable hinge. I start in the same way, blocking out the basic form. Only this time I cut out these middle faces. At this point I realize that I can cut the model in half and mirror it align the y-axis, reducing the workload by another half. Next I need to fill these faces, and create the supporting loops for the edges, so I select the edge loops, bevel to create good neighbors, and mark creases. Here I realize that the supporting edge should continue over to the mirrored geometry at the points where the original and mirrored meshes connect, so I manually extend the loops. Then I do a bit more tweaking with the extruded edges, in the same way as with the other hinge. Now I can move on to dealing with the inner area. This loop needs to be beveled manually, so that the subdivision isn't controlling the curvature, and then I simply connect the diagonal edges to maintain a quad topology. You'll see me looking for the Smooth Vertices option in the Mesh menu. This is a pretty useful tool. I suggest you add it to your quick favorites. After beveling these horizontal edges, and dealing with the bottom faces, this hinge is finished. This shows you how peaceful yet intricate the modeling workflow can be when you understand what is going on behind the scenes. However, this workflow can be exhausting and time-consuming. A great tip I was given is to set a timer so that you don't end up spending too long on a small mechanical piece. I would add to that by making sure you set up timers to take breaks if, like me, you are prone to getting carried away when modeling. Let's move on, making a new piece that can connect to this hinge. As usual, here is some reference if you want to try to make it, but feel free to make anything, as long as it connects to the hinge we made. Now let's go through the modeling process. The first thing I did was spawn a new cylinder and made sure, using snapping tools, that it perfectly fit within the hole of the hinge before adding a mirror modifier. I then began extruding and preemptively beveled and creased some edges, making adjustments to the base mesh. Keeping in mind the lightweight design, I cut out some of the mesh, making sure I was controlling the curvature of the concave geometry. I knew I wanted to cut another cylindrical hole at the top of this piece, and was deciding whether I should localize some geometry for it, or add edge loops. I chose to add edge loops, as it seemed the extra edges added from localizing would almost counteract the localized geometry, not making it worth my time and effort. Over here I used the shear tool to rotate the geometry without any distortions, before cleaning up some supporting loops, filling the top faces, and adding a more intricate design to the outer cylindrical area. Now we have two lightweight, interlocking mechanical pieces. Let's add one more, before looking at what more we can do with hard surface models. Here are the references. As mentioned, hinges are common for rotations on one axis. Rotations on all three axes usually require some sort of ball joint, but two-axis joints can be very interesting to model. Just like with hinges, there are an infinite amount of ways you could design these joints. For this example, I will design one that includes a curved shape, so that we can practice performing booleans on complex mechanical pieces. It is actually made of two pieces, a ball that rotates on the x-axis, and the piece going through it, that rotates on its local z-axis. I start by spawning a round cube in the center of the holes made in the previous piece. Here I'm making boolean cuts through the holes, into the round cube, making sure to mirror the detail so as not to do it twice. Now, in the same way I need to cut a hole through the round cube vertically, being careful to avoid the other dents that I just made. After cleaning the mesh up again, I begin adding loops and creases to the mesh, before extruding out some handles to connect it to the previous piece. To create the next piece, I duplicate and separate the inner cylinder, extrude out the basic form, and add some 45-degree shears, which continue the design of the identical shears created earlier. Finally, we have this four-piece mechanism, all with perfect topology, great subdivision, and consistent design. This exercise was similar to ones we have done in the past, where we freestyle, starting from a plane and adding extrusions, cuts, and localizations. Only this time, we are freestyling entire mechanical systems. It takes a lot longer, but is an amazing way to gain experience and practice. Let's see some final points before ending the series. Once you've finished the model, unless you are unsure and might want to make changes later, you can apply the mirror modifiers and join the meshes. Note that when rigging, some people prefer keeping the objects separate and parenting each one to a bone. My method is usually to join all the meshes and use weight painting to assign meshes to bones. It's really up to preference if you want to join the objects or not, but if you do, it makes it easier to now manipulate this mesh. With all the objects joined, you can easily add modifiers like arrays and mirrors to multiply the detail. Since our mesh has perfect quad topology, we should even be able to use something like a simple deform modifier. Messing with the options gives some unique results that would be very difficult to model manually. Another topology-dependent modifier that you can try out is the wireframe. If you have a quad topology, the generated wireframe should be accurate. Just be careful with subdivision modifiers, the results can get very heavy. The point to take away from this is, finishing the modeling process is not always the final step in creating a hard surface model. Finding ways to add more detail with modifiers can boost the quality of your models with little effort. However, if you are going to add modifiers, it is usually best to apply any instancing or deformative modifiers before texturing, rigging, and animating. If you don't, you may have issues exporting your models to other programs like Substance Painter for texturing, and rigging and animation can be difficult when you still have instances being mirrored or arrayed along empties. The final tool I think you should know about is the Asset Browser. If we rename this object to something like Mechanical Piece 1, and then mark it as an asset, we can open a new window, set it as the Asset Browser, go to the Unassigned section, and there you will find this object. You can use it in this project as many times as you want, dragging and dropping it from the browser. I highly suggest you have one project where you make a lot of miscellaneous mechanical pieces, as well as materials, and save them as assets. If you want these assets to appear in every Blender file, you can go to Preferences, and then File Paths, create a new library, I called mine Mechanical Pieces, and find the folder where you saved your project. Blender will automatically take any assets marked in this project and add them to your asset browser. You can organize your assets by selecting the asset library in this drop-down, in this case the Mechanical Pieces library, pressing the plus icon at a catalog, rename it, and drag in your asset. Now in another project, I can open the asset browser, navigate to the Mechanical Pieces folder, and drag in the object. You can choose to link or append assets that you drag into your scene. Linking assets will not allow you to edit or change anything about them, including any assigned materials. Appending assets basically creates a copy that you can freely edit and even mark as another new asset. Having a custom asset library of mechanical pieces will help you kit-bash hard surface models and greatly speed up your workflow. It is also good practice. You can always expand your custom library and hop into this project whenever you want to relax and make some miscellaneous mechanical pieces. And that's it. We have completed all 8 sections of this series. Let's celebrate by looking back at each section and revising what we have learned. In Section 1, I introduced you to the idea of tools and techniques with the example of Booleans and the circle tool. In Section 2, we began delving deeper into understanding subdivision and the Catmull-Clark algorithm. In Section 3, we learnt about creases and how the 2 effects of the Catmull-Clark algorithm can be overcome, providing us with the basic knowledge required to make some complex models. Section 4 was all about modeling techniques. With all the knowledge we had gained, it was important to take a breather and develop some good habits before moving on to more advanced methods. Section 5 was tough. With our understanding of tools and techniques, we were able to classify the process of localizing topology, but learning all of its ins and outs requires a lot of practice. Section 6, orientation and snapping tools are a foundation of precise hard surface modeling. In this section, Blender showed us how advanced and deep these tools have become. In Section 7, we learnt about the purpose of curves in the hard surface workflow, how to model and map patterns onto them, and went a step further by exploring the rigging method for curves. Finally, in this section, Section 8, we brought all our modeling knowledge to the table and made a mechanical system. I then showed you how to work with asset libraries and the asset browser to take your workflow from an amateur to a professional level. I hope you enjoyed the series. This has been my passion project for the last few months, and I'd be really happy if this series performed well. As I've said, I'm excited to potentially work on a sister course on rigging, possibly releasing sections weekly or every few days. If you feel that you learnt a lot from this series and want to see more, please share the series, like, and subscribe to show your support. So, that's all. Thank you for watching, and I'll see you in the next video.